All right, little chickadees, here we are today, ready to do Note 7.2, Direct Substitution. The notes are long, but the concept is actually pretty easy. So here we go. The objective for today is to use the properties of limits in direct substitution to evaluate limits. So when evaluating limits, there are several ways to solve most of the problems. The most common ways we're going to solve limits would be graphically, which we talked about yesterday. So if we have a graph, we can evaluate the limit coming in from the left, the limit coming in from the right, and the overall limit of the function. We can do it tabularly. So what does this word really mean? Basically using a table. So I think 7.3 tomorrow we will talk about using a table to evaluate limits and just looking at the whole numerical analysis and analyzing the numbers. And the last way, probably most common way, is direct substitution, which we are going to talk about today. So if we want to apply direct substitution to the definition of a limit, so if we look up here at the top of our screen, we have the limit of a function as x approaches c equals f of c. So if we talk about what does this really mean in the English language, it means if the function is continuous at the number c, so 5, -10, 27, whatever number c is, then we can take and substitute c into the function and find what that function is approaching as x approaches c. So another key word we probably need to discuss is this word right here, continuous. So a lot of the algebraic functions that you have talked about in the past are continuous functions. A line is a continuous function, a parabola is a continuous function, a sine function is a continuous function. So basically these functions can be drawn from left to right and have a domain that goes from -infinity to infinity. There are no breaks in these graphs. So if we were to pick a point on this graph, as we come in from the left and as we come in from the right, we are approaching the same exact y value. So as long as the function is continuous, it is going to be continuous at every single point from left to right. You can just substitute the number into the function and you can find this y value right here that we are approaching from the left and from the right. There are also functions such as rational functions. So if I take a second and draw a rational function, okay, so here we have a vertical asymptote when x equals 0. So when I look at my function, there is no limit when x equals 0, because when I come in from the left and I come in from the right, this graph is doing two different things. One side of my graph is increasing while the other side is decreasing indefinitely. However, if I think, okay, you know what, I want to evaluate the limit of the function as x approaches 5, well, if I come over here to x approaches 5, the graph is continuous at 5. So even though the graph as a whole is not continuous because we have a big fat break and we have to jump over the vertical axis, at 5 this graph is continuous. So as I come in from the left and as I come in from the right, I approach whatever this y value is. All right, so if we look at example 1, it says use direct substitution to evaluate the following limits. How does the solution relate to the graph? All right, so the first thing I'm going to do is graph 3x plus 2. So I'm going to have to bust out the old knowledge of linear functions. So the 2 is my y-intercept, and I have a slope of 3. And I have my graph. So I see every line is a continuous function, so the limit as x approaches 4, I can plug in this value right here, and the limit, and yes, you have to bring that down every single time, the limit as x approaches 4 of the function is going to be 12. So basically we're saying that the limit of 3x plus 2 as x approaches 4 is equal to 12. So our y value is approaching 12 as x approaches 4. So somewhere way up here, I have a y value of 12 as x is approaching 4. All right, so now I look at my next graph. It's an exponential function, so I have a y-intercept of 1, and since my base is 4, this graph is approaching or increasing to infinity relatively quickly. So I can come in here and I can say the limit of the function 4 to the negative 2 as x approaches negative 2, and the limit is going to be 1 over 4 squared. So the limit as x approaches negative 2 is going to be 1 over 16. So for this function, as x approaches negative 2, the y value approaches 16. And we should really write our final answer. Limit as x approaches negative 2 of my function is going to be 1/16. Okay, moving on. We have some basic limit properties. So the next slide, couple slides, I need to go over them. They are not super hard, but we just have to establish the rules of limits basically so that we're all talking the same language. So the biggest keyword I see going on right here is we have a constant function. So when I look at this, there's no variable involved. So anytime I have a constant function, the limit is just going to be whatever that whatever that number is. Whatever that number that is, because this is just a horizontal line. So if we think of the graph of 12, we have this line that crosses the x-axis at 12. So no matter what, every single y value is 12 forever and ever and ever. All right, so we have the limit of the identity function. So the identity function you identify with yourself. So if we graph this function, we have a function where it's this straight diagonal line, 45-degree angles. When x is 1, y is 1. When x is negative 5, y is negative 5. So here, if I simply substitute in negative 3 for my x, the limit as x approaches negative 3 is simply going to be negative 3, because over here at negative 3, I also have a y value of negative 3. All right, so when we have a power function, so x raised to a power, it's basically going to be, I can substitute that number in, and if I, in this case, substitute in negative 4 cubed, I'm sorry, that's not negative 4, that's 4. So if I have 4 cubed, 4 times 4 is 16, 16 times 4 is 64. So you're able just to substitute in the function, and you're good to go, because once again, this is a continuous function. X squared, x cubed, x to the 4th, all continuous. And then my last basic limit property is my square root property. And again, the square root or the nth root, a square root would look like this. Okay, so it's still a continuous function. It doesn't exist over here to the left of my y-axis. It only exists when, it only exists when x is greater than 0. So if we think about the function cube root of x as x approaches negative 125, this is really going to be the cube root of negative 125. And we can take the cube root of a negative number, because this is saying that negative 5 times negative 5 times negative 5 would actually give me a negative 125. Remember, when you have rational exponents, you take the square root, or you take the root of the denominator. So this can actually be written as the 4th root of 64. And if I think of 64, 64 is 8 times 8, which isn't the 4th root. But if I continue to break that down, I get 4 times 2, and 4 times 2, and 2, and 2, and 2, and 2. So this is really going to be 2 to the 6th. Need a little more space here. And so if I take the 4th root of 2 to the 6th, what I can do is 4 goes into 6 one time, so I can take out one of those 2's, and it still leaves me with 2 of those 2's in there. So I really have the 2 times the 4th root of 2 squared, or you can say 4 times the 4th root of 4. All right, so continuing to move on. So we have some properties of limits, and that is what I'm going to cover next. So when we look at these properties of limits, the first one is going to be our scalar multiple. This definition is going to be on every slide for the next 5 slides. So right here, we have some conditions. It says B and C are real numbers, and N is always going to be positive and positive integer, and F and G are just functions with the limits. Okay, so as x approaches C, f of x is going to approach L, and the limit as x approaches C of g of x is going to approach K. So what does a scalar multiple mean? A scalar multiple essentially means we have a scalar or a number out in front of my function. So in the end of the day, this means that we have the limit of b times f of x. They are going to take this b right here, and they're moving it out front. So if you look right here, this b is out front. Now we have the limit of f of x as x approaches c, and if you look up here, the limit as x approaches c of f of x is L. So in the end, this just turns into b times L. Essentially, that is a very complicated way of saying, hey, if you look at this example, we got the limit as x approaches 4 of 9 times 4, or 9 times x. We can really substitute in 4, and we get 36. So this is kind of like saying, hey, the limit as x approaches 4 of x, and then we can bring this 9 out front. So this is one of those basic properties in the identity property, but we could bring that 9 out front and isolate that, and that's kind of what this scalar multiple property is saying. All right, the sum and difference property. So again, if you look right here, everything here is behind the limits. So all of the good stuff is behind the limits. If you look and we compare step 1 to step 2, now we have taken the limits and we have separated them. So by our definition, the limit of f of x as x approaches c is L, and the limit of g of x as x approaches c is k. So this is really going to be L plus k. How does this apply to a real problem? So we have the limit as x approaches -2 of 3x squared minus 4x. So this is really the limit of as x approaches -2 of 3x squared minus the limit of x approaches -2 of 4x. We could use our scalar property, our multiplication property, and move the scalar 3 and the scalar 4 out front. But at this point, you can really just do direct substitution. So if we substitute in -2, this is a quadratic function, and because a parabola is continuous over the entire domain, I know that it's continuous everywhere, so I can just do direct substitution. 4x is a line, and it's also continuous over the entire domain, so I can also do direct substitution. So I don't have a calculator, so I get 12 plus 8, and in the end, this is going to equal 20. All right, so another property of limits. Now we're to the product property. So again, if we look, f of x times g of x are all behind the limit. You can separate those two things out and multiply them together. So just like before, the limit of f of x as x approaches c right here is L, and the limit of g of x as x approaches c is k. So you're just going to take L times k. So if we look at this limit, I can break this apart, and I can take each part individually. So the limit as x approaches pi of pi times the limit as x approaches pi of cosine x. And now I can just isolate those. I know that the limit of x, this is a line, so I know that I can just substitute in pi, and I get pi So that's not a diagonal line, it would be a horizontal line. And then times the limit as x approaches pi of cosine x. Well, I also know the cosine x is a continuous function. So I can take the cosine of pi. This is going to make you really think because we haven't done cosine in a while, but the cosine of pi is right here. And so the y value when the x value of pi is -1. So this is really pi times -1 or negative pi. All right, two more of these. We got the quotient property. So in the same sense of everything that we've been doing, we're just going to take the limit as x approaches c of f of x over g of x. We split them into two separate limits right here into the numerator and the denominator. And this gives us L divided by K. We do have a condition here that g of c, so whenever we plug c in, it cannot equal 0 because there's no division by 0. So we do have to watch for that because that will pop up in rational functions. Got an example. We see tangent. We love tangent. So I can break this apart into the limit of tangent x over as x approaches pi all over the limit as x approaches pi of x. So this will really turn into the tangent of pi over pi. And if I think about the tangent of pi, the tangent of pi is going to be 0. And 0 over pi is going to be 0. All right, and if you can't remember the tangent of pi, just remember, here's pi halves, and for tangent, here's pi right here. So the y value at that point is 0. Awesome. All right, so now we have our power function. So the limit of a function being raised to the power of n as x approaches c. So I can just take and say, all right, I know what this is. This is all L, so this is just going to be L raised to the nth power. And as long as our function is continuous, we can essentially use direct substitution. So this is really going to be 3 plus 4 to the n power, and not to the n power squared in this particular problem. So 7 squared, which is 49. Okay, the next two properties, the limit of a polynomial function. If p is a polynomial function and c is a real number, then the limit of p of x as x approaches c is p of c. And the reason this happens is because the function is continuous. So I've kind of been hounding that the whole entire. Okay, so the limit of a rational function, if r is a rational function, r of x equals p of x over q of x, and c is a real number, we have this constraint right here that q of c cannot equal 0 because that will make my denominator 0, and there is no division by 0. So the biggest thing here is whenever we plug c into our function, if it makes our denominator 0, we cannot do that. So that is a problem, so be watching for that, be watchful for it because it does pop up. Other than that, we can plug and chug and find our limit. So as long as we're not looking at a number that makes our denominator 0, that rational function is continuous everywhere else, and we can evaluate the limit. What does that rational function look like again? It could look something like this. So you have a piece here, and you have a piece here. So right here at c, this function, the limit does not exist because as you come in from the left, we are decreasing, and as we come in from the right, we are increasing, so we do not approach the same exact value, but everywhere else on that function, we are continuous, and we can evaluate the function. All right, two more examples. So when you see your examples, just kind of picture what the graph looks like. So evaluate the limit by direct substitution. This first function is quadratic, so it's because it's a parabola. I don't know if that's the correct graph, but it's a parabola, so it's continuous. So I can really just substitute in -1. So 1, -3 times -1, and in the end I get 11. So the limit as x approaches -1 of x squared minus 3x plus 7 equals 11. Yes, you really need to write this whole limit statement because it tells us that we are approaching -11, not necessarily equaling -11. And yes, because this is a parabola, it does equal -11, but because they have asked us to evaluate the limit, we're talking about the value it approaches. All right, b is a rational function, so I definitely need to make sure if I plug 3 into the denominator, do I get 0? No, I don't. So that's a good thing. So now I can simply substitute 3 in. So 2 times 3 squared plus 4 times 3 minus 12 all over 2 times 3 minus 5. And 19 minus 12, so we get 7 over 1. So the limit as x approaches 3 of this function, 2x squared plus 4x minus 12 all over 2x minus 5 is, oops, did I get a wrong answer somehow? 4 times 3 right here. I'm sorry, that is 12. 12 minus 12 is 0, so Ms. Schwartz made a mistake doing too much math in my head too fast. So this becomes 18 over 1. I apologize for those of you who are rapidly copying as fast as I write and as fast as I talk. Okay, so at the end of the day, as long as you don't have division by 0, when you substitute a number in, you can do direct substitution to evaluate the limit, and it truly is the easiest way to evaluate a limit. We must have a continuous function, so I don't care what your function looks like, as long as we're coming in from the left and we're coming in from the right and it's continuous, the limit is going to exist. All right, you listen to me for 22 seconds, you deserve a break. Homework will be easy in class tomorrow, so I look forward to seeing you and have a wonderful night.